Hello, my name is Jared Skeens and welcome to the Zoom room. Today we want to look at Pure Maths 1, Differentiation, Part 5, Rates of Change. So in the previous parts, we looked at how the first derivative can be applied to different concepts of slope. What we want to look at in this part 5, is how we can use these differentials in a different way other than slope. So to illustrate that, I just have a basic graph here at the bottom. And so again, this red curve represents our function of x. And notice instead of, we still have x and y axis. And so here we have a point on the curve, and this point is going to be moving along the graph. So as this point moves from this first spot over here to the second spot, it's going to be covering some distance along the x-axis, and it's also going to be covering some distance along the y-axis. So here you can see as it moves from this point up to this point up here, you see the change in x-axis, you see the change in the y-axis value. Well, there's something practical to real life that needs to be considered, and that's the aspect of time. So if this point is moving, it doesn't get there instantaneously. It takes time for it to move from this position over here to that position. So when we look at our change in the x value, or we look at our change in the y value, we want to look at it with respect to time. So we're introducing a third differential. So this dy or dx or dt, they're called differentials. And the dt especially is called a parameter. Parameter just means alongside measurement, like a parachute is a chute that goes alongside of you when you jump out of airplane. So a parameter is alongside measurement. So we have our x and y axis, which we normally use. Now we're bringing in time as this parameter, this alongside measurement. And so as we look at the change along the x-axis or the change along the y-axis, we're looking at it with respect to time. So that's going to create a little bit different options for us than purely looking at the algebraic concept of slope. Okay, so for our first example, here we have an equation, y equals 2x plus 5 over x. Now again, this will give some sort of a curvy graph, but we don't get to see it. And it says that the x coordinate is increasing at 0.02 units per second. Notice it is a rate, units per second, two units in a fraction. So it's increasing at 0.02 units per second. We need to find our rate of change for the y coordinate at x equals 1. So this one is important up here. And basically, these rates of change, it's kind of like speed. Speed is distance over time. The change in your horizontal position divided by the change in time gives you speed. So this is kind of like speed. It's speed along the x-axis and speed along the y-axis. So what we need to recognize is that this x-coordinate increase, that is your dx dt, because units per second, and it's for the x. So dx dt equals, and increasing means it's a positive. Decreasing would be a negative. So it's a positive 0.02, and it's units per second. Then we need to find the rate of change. So again, because it is a changing rate, meaning this rate of change is not consistent all through the curve. For example, if this were a roller coaster, well, the roller coaster would be going up the hill more slowly, but then when it went down the hill, it would be going faster. So the rate of change depends on its position. So we want to find the rate of change for the y-axis value when x is at a particular point, being 1. So because we're dealing with rates of change, and calculus deals with changing concepts, then we want to do the first derivative. So, but when we do the first derivative, we're not going to use our normal notation. We're not going to use the prime anymore. Now we got to keep track of these differentials separately. So it adds a little twist. Your derivative formula is the same, but when you derive y, you get dy. So don't just put y prime. We need to see our differentials. So the derivative of y is like 1 dy equals, now this is 2, but our variable is x. That means this is a 2 dx. So every time you do the derivative to a variable, you get the differential dy, dx, so on. Now this is like a 5x to the negative 1. Okay, this is the same thing as 5x to the negative 1. Okay, so we multiply, we get a negative 5x to the negative 2. So we multiply to the front, subtract 1, and then again we get a dx. So if we factor out the dx, we get dy equals 2 minus, this would be 5 over x squared, and factor out the dx. Now we're going to introduce the dt, the change in time, simply by dividing both sides by dt. So as long as you multiply or divide both sides by the same value, then you're maintaining your equation. So over dt and over dt. So we introduce the parameter. Now we can see how y changes with time and how x changes with time. So it's asking us for the change in the y coordinate, meaning we're looking for dy dt. So dy dt is going to equal 2 minus 5 over, and it asked us for at the point where x equals 1. So remember, the rates of change can be different along different parts of the curve. So we want to find it at one particular point where x is 1, so 1 squared, times dx dt, which is a positive 0.02. So here we end up with 2 minus 5. That's a negative 3 times 0.02 gives us a negative 0.06. So there's two ways that you can give the answer. You can say dy dt equals a negative 0.06 and just write the numeric value. Or you can say that dy dt is decreasing at 0.06, or a rate of 0.06, again, units per second. So you need to either show the negative sign or you need to say that it's decreasing. You should not put the two together. So it's either changing at a negative value or it's decreasing at, a positive value. So make sure you're careful, but either way is acceptable, this way or this way here. So this is our first example. As a particle moves along this curve, the x coordinate at a particular point is changing at this rate, and so we're finding the rate of change of the y-axis change at the same location. Okay, so let's set up another example. Okay, here's our second example. Notice for this example, they actually already give us the derivative. So they give us dy dx equals x cubed minus 4 over x squared. Again, you always want to pay attention to where you're at in this flow of thought. So this is already the derivative, but it's in change in y in terms of change of x. And there's a point P at the location 2, 9 that is on this curve. And it tells us that the x coordinate is decreasing at a rate of 0.05 units per second. So here we have a point, our x value is decreasing at 0.05, and we want to find our rate for the y coordinate at P. Well, notice that our rate has time in it. So anytime you see a rate and it asking for a rate, you need to think differentials or derivative. So we already have the derivative, but we need to rearrange our differentials because this wants it units per time, not y per x. So we need to multiply our dx to the other side. So this is going to become dy equals x cubed minus 4 over x squared dx. And this should make sense because you notice that the dx comes over here with the x terms, and the dy is over here where the y usually is at. So we've had to separate the differentials, and now we can introduce the time differential. So we'll divide both sides by dt. That way we create our rate. And it's asking for the y coordinate, which means dy dt. So we're already set for that. So our dy dt equals, it's at point P, meaning we want, and we have x variable here, so we want to use the x coordinate of point P, which is 2. So we plug the 2 in for the x, and we get 2 cubed minus 4 over 2 squared times dx dt. Now remember, it's decreasing. That means it's a negative. So times a negative 0.05. And so this becomes 8 minus 4 over 4 is 1 times a negative 0.05, which equals 7 times a negative 0.05, which is a negative 0.35. 5 times 7 is 35 with 2 decimal places. So you have 2 ways, again, that you can show it. You can say that our rate of change of the y, so our dy, or the change of our y with respect to the change in time, is at a rate of negative 0.35 units per second. Or you could also say it's decreasing at 0.35 units per second. So it doesn't really matter. Again, you have to put one of them, either decrease or the negative. And it's units per second. So the y-axis, 0.35 units along the y-axis per 1 second of time. So we did an example for increasing. Here's an example of decreasing. Now we want to look at a couple of examples that are a little bit more like story problems on how to apply it to a situation, not just the algebraic function itself. So let me set up another problem. Okay, here's our next example. Here you see that we have this rectangular prism, kind of like a box. and the height of this box is x centimeters tall. It's 2x centimeters wide and 4x centimeters long. So in the first part, it wants us to show that the relationship between the surface area and the volume can be expressed with this equation, S equals 7v to the 2/3 power. So that's our first task. So it's a little bit of an algebraic geometric task. So we'll start with surface area. Okay, so our surface area is going to be, well, the front panel, remember it's area, surface area, so it's just height times width here. And there's a front one and a back one, so this front one and back one here. So there's two panels that are x times 2x, or 2x squared. So that gives the front and the back. Plus, there's the top and the bottom. So that's two more panels that are, the top and the bottom is 2x wide by 4x long. So that's 8x squared. Plus, we have the sides, one on this side and one on this side. And that is x, because this is also x right here. So x by 4x. So there's two of those, right side and left side. And so that's 4x squared. So again, we have surface area, means all the area added up. So there's two, the front and the back, that's x times 2x, or 2x squared. There's the top and the bottom, so that's 2, that's 2x times 4x, or 8x squared. And then another 2, that's the left and right sides, that are x times 4x, which is 4x squared. So this gives us a total of 4x squared plus 16x squared plus 8x squared. So we get a total of 28x squared centimeters squared is our surface area. If we look at volume, volume is simply length times width times height. So x times 2x times 4x will give us volume. Width, length, height is volume. That gives us 8x cubed. Now it wants us to make a relationship between the surface area and the volume. So what we can do is we can solve for x in terms of volume and plug it in here. So if we solve for x, if we get x by itself, we first have to divide by 8. So that's 1/8 of the volume. So we divide both sides by 8. Then we need to cube root it. So cube root the 1/8 v. Okay. Now we want to plug that in here, and we get S equals 28 times this 1/8, or cube root of 1/8. Let's get the cube root in there. The cube root of 1/8 v, and this is squared. Okay, so we plugging this x into here. So the cube root of 8 is 2, squared is 4. So what we end up with is 28 over 4. Cube root of 8 is 2, squared is 4, and we get v to the 2/3 power. So this reduces to 7v to the 2/3. Okay, so that's the first part. Okay, now for the second part, it says to find the rate and change of the volume. Okay, that means we need to do a derivative so that we get that dv dt, because it's the rate of volume, change of volume with respect to time. So we need to derive this. So when we derive the S, we get ds equals, now I'm working with S equals this, so our parts are right here. S equals 7 v to the 2/3. So now we have to multiply the 2/3 to the front. So that's 14/3. Subtract 1. 2/3 minus 1 is a v to the negative 1/3. And then the differential, which is dv. Okay, and now we can add our dt here. So divide by dt. There's our time part. Now we have the rate of change with respect to time, and it wants us to find for the volume. So our ds dt, right here, our s is increasing at 2. So the ds dt is 2 equals 14/3. And then we have 1 over, because this is a negative here, meaning it's downstairs, the cube root of v, which is 1,000. And then we have our dv dt. So what that gives us is, this is 1 over 10. The cube root of 1,000 is 10. So we get 14. This over here is 14 over 30. So when we multiply and divide to the other side, we get dv dt equals, times by 30 and divide by 14, we get 60 over 14, which equals 30 over 7, which you can leave it as 30 over 7, or you can change it to 4.29 to 3 significant figures. So either one of these is fine. So what this is saying is, as the surface area, as this 2x to the x squared, as this surface area increases by 2 centimeters squared per second, the volume of it is increasing by 4.29, and this would be volume. So your units on this would be, let me get rid of this 3 significant figures, would be cubic centimeters per second. So 2 area centimeters, or 2 centimeters squared per second, translates into 4.29 cubic centimeters of volume per second. So a little bit more of an application there. So let me give you one more of these types and see how you do. Okay, here's our last example. And here we have a bowl, the cross section of a bowl that is filling with water. So as you can see at the bottom part of the bowl, the bottom part is narrower. So when you put water in, the height is going to go up a little faster. But as you get towards the top of the bowl that's wider, which meaning it takes more water to fill that slice of area, then the height will be increasing more slowly. So the rate of change of the height as you add water into it will be faster at the bottom, slower as you get to the top because it's getting wider. So this bowl, the volume of this bowl of water, is expressed by the equation V equals pi times 1/2 h squared plus h. So the volume in terms of height. And now it says that the water is poured in. So you're pouring water into this bowl. And as you pour the water into the bowl and it fills up the bowl, the water level rises. So it doesn't actually tell you which variable you're dealing with, but you need to pay attention to like water being poured in, that concept. Is that a linear concept? Is it an area concept? Or is it a volume concept? Well, if you're a little confused by the English words, look at the units. Notice it says poured in at 2 centimeters cubed per second. This is a cubic unit, meaning it's volume. So this is talking about the dV dt. dV, the change in volume per unit of time, is 2 centimeters cubed per second. So our volume is increasing by 2 cubic centimeters for every 1 second of time. Or that's basically consistently, but again, the height is going to change differently. You can pour in the same amount of water consistently, but because the bottom is narrower and the top is wider, the change in height will not be the same throughout the entire bowl. So find the rate in centimeter per second for the height, and notice it's increasing when h equals 3. So since we're dealing again with rates, we need to find the derivative. So dV equals, now the pi is just a constant, so we can just leave that in the front and not worry about it because it's in the front of this parenthesis. H is our variable, so 2 times 1/2 is just 1. Subtract 1 from the exponent gives us h, and then we have a plus h, meaning we get a plus 1. The derivative of h is just 1. So the exponent's 1 times 1 is still 1, and then 1 minus 1 for the exponent, 0, the h goes away. But then our differential, dh, don't forget the differential goes with the variable. Then we can supply our dt, our time. Okay, so the change in volume with respect to time and the change in height with respect to time. We're looking for the change in height with respect to the time. Notice it gives us centimeter per second. Height is a linear concept, one-dimensional. So centimeter as opposed to volume is cubic, centimeter cubed. So the 2, which is being added, so it's increasing volume, so it's a positive 2 equals pi times, and remember I said that our change in height depends on where we're at. At the bottom, where it's narrower, the height is going to increase more quickly. At the top, where it's wider and it takes more water to fill that space, the height will decrease more slowly. So where we're looking at is where our height equals 3. So we want 3 plus 1, and then our dh dt. So this is 2 equals 4 pi dh dt. So our dh dt equals 2 over 4 pi, which equals 2 over pi. Now, or sorry, not 2 over pi, 1 over 2 pi. 2 and the 4 cancel, leaving the 2 on the bottom. 1 over 2 pi. And then this doesn't really connect to our thinking because it has pi in there. So if you want, you can convert it. This is approximately 0.159. You can do it on your calculator. 1 divided by 2 pi. 1.59 centimeters per second. And it's positive because the height is going up. As you add water, the height goes up. So it's increasing, and it already said increasing over here. So it's increasing at a rate of the dH dt, 0.159 centimeters per second. So here is our second practical illustration. What's important for these Cambridge questions is that you recognize these verbal clues, these rates of change where you have 2 units where time is on the bottom. That means you got to work with the differentials. You got to keep them separate. It's not always X and Y. Sometimes it's volume and height or volume and radius. It doesn't really matter. Your derivative formula is the same. It's only the variables that change. Keep the dv with the derivative of v, the dh with the derivative of h. Then once you have them separated, you divide both sides by dt. That's our parameter, our alongside measurement. Now you have a rate with respect to time. It makes the math application much more applicable to real life situations because life goes by time. So here's our rates of change. This concludes our unit on differentiation. So the first part one was how to do the derivative and the concept of the derivative being mainly algebraic slope. Then part 2, 3, and 4 were various slope applications. And now part 5, this rate of change application using the differentials. So again, thank you for joining me and see you again next time.